Hello, this is assignment number 9 on a chapter about rotations. Question number 1 has to do with the calculation of a rotational inertia, and to calculate rotational inertia you need to add the masses of the system times the distance squared that the masses are from the axis of rotation, and this distance is the perpendicular distance. So in this particular problem, you can calculate the rotational inertia around this axis, for example. And around this axis, only this mass and this mass can rotate. This mass cannot rotate around this axis because it's on the axis. And the distance are this one and this one. And these distances are given here depending on which coordinates you are using. If you want to rotate around the y-axis, then this mass now contributes with this distance, this mass with this distance, and this mass with this distance. And if you want to rotate around the z-axis, which is the axis perpendicular to the plane of the page, then the three masses can rotate around, and the distance for B will be that one, the distance for A will be that. You have to convince yourself that these are the real distances, and all of that is just from the geometry of the problem. A very similar situation you are going to have in problem number 2. Now when you have four masses arranged here, in this situation, when the axis, this mass does not contribute, this mass does not contribute. So the rotational inertia will be the mass times this distance squared plus this mass times this distance squared. Around these two do not contribute. These two do, because they rotate like that around. But the real distance is this distance. And you get that distance from the geometry again. And around this axis here, that is perpendicular to the page, all the four of them can rotate around. And the real distance that you are considering is this thing that is easily calculated from the geometry of the problem. So a lot of Pythagoras theorem in here. Let me go to number 3. Number 3 and number 4 are calculation about torque. Actually, number 3 is an example of number 4, because in number 3 the weight is, in this particular case, perpendicular to the distance. So the torque, remember, is the force times the distance that the force is applied to the point you are calculating the torque times the sine of the angle between the two. So if they are perpendicular, like in problem number 3 or in problem 4a, then the torque is nothing more than the product of the force times the distance. If they are parallel, then the torque is always 0. And part B, there is a case in between in which you have to consider the sine of the angle. This system, in order to be in equilibrium, the sum of the torque around any point has to be 0, and the sum of the horizontal forces, it has to be 0, and the sum of the vertical forces has to be 0. This condition has to be satisfied around any point, in particular around this point. It cannot rotate around this point, therefore this mass tries to rotate it in this direction. So this rotation is counterclockwise. This one tries to bring the system in this direction is clockwise. The sum of these two are up 0, so this is equal to this, and this is Fr, and the other is omega r, and there you have it. Similarly, you have this situation of the painter here. The painter, this is the situation you have. The free body diagram for the platform is as follows. Is the force on the right, the force on the left, the weight of the platform, and the weight of the painter. This is actually the normal force, but it's happened to be equal to the weight of the painter. So now, if you want to calculate, for example, this force, you can demand that the torque around here be 0. And if the sum of the torque around there is 0, this torque is clockwise, and both of these are counterclockwise. So this one, if you know this distance, and you do, is equal to the sum of these two with their respective distance. And D2 and D1 are given, because all of these distances are given in some way or the other. Then you can go back and add the forces equal to 0, or you can do the torque around this point. Many choices. Same thing happened with the problem of the painter. In this particular case, what is interesting is that, again, the free body diagram is for the ladder. And for the ladder feels a force from the wall, this force N, and also feels a pull from the floor. Those are the only horizontal forces on the problem, so the force of friction is equal to N. So if you want to find this, you just need to find that. And that you find with the torque, because, of course, the ladder has a weight, and it's also experiencing a force here, which is equal to the weight of the painter. And even though there are some vertical forces here too, around this point, for the system to be in equilibrium, you have to demand that the torque be 0. Now this one tends to do that. So this one tends to go counterclockwise. These one around this point tend to go in this direction, and these tend to go in this direction. So both of these are clockwise. So this torque is equal to the sum of these two. And this one, the lever arm is just this distance that is given here. Then the only distance that you need is this distance that you can get from the geometry, and this distance that you can get from the geometry. You can calculate the angle given the geometry. So it's all very similar to the previous one. It's just geometry. The torque has to be equal to the rotational inertia times the angular acceleration. So you can calculate the torque if you calculate the rotational inertia, and this is very similar to the previous problem in which these are the real distance. So that should be straightforward. So you're in a merry-go-round and you want to push in this direction and then you push in that direction. Then if this is F and this is F, this is a torque in that direction clockwise, this is also clockwise. So they are up. And that's equal to that times alpha. And then you can get that, and then once you get alpha, you can go to that, you can get what will be the angular velocity. And we did this in lecture, in which we find out that mg is going to, for an sphere, because of the beta, look at the lecture notes, this is the condition. So in this particular case, all of this energy is going to go into potential energy. So thank you very much.